Hello, and welcome to our lecture on trigonometric identities. In today's lecture, we'll develop some formulas involving trigonometric functions and relationships between these functions. These are used quite a bit in calculus classes to simplify expressions involving trigonometry. And before we get started, let's review some of the formulas, some of the identities we've already looked at in this course. For instance, we defined sine, cosine, and tangent, and then observed that secant was the reciprocal of cosine, 1 over cosine, cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. And then we came to perhaps the most important identity, sine squared of u plus cosine squared of u equals 1. By identity, I mean the following. For every real number u, that equation is true. For every u in the real numbers, that's a true statement. That's what an identity is. And from that identity, we developed a couple more. Tangent squared plus 1 equals secant squared. How did we get that? Well, we divided both sides of the fundamental identity by cosine squared. And if you remember that computation, it gave rise to tangent squared plus 1 equals secant squared. And in a similar fashion, if we divide both sides of the fundamental identity by sine squared, we get 1 plus cotangent squared equals cosecant squared. That identity is not quite as important as the tangent squared identity I just talked about. And then we had some co-function identities. You might remember that we observed that sine of pi over 2 minus some angle u equals cosine of u. In other words, co-functions of complementary angles are equal. Cosine of pi over 2 minus u equals sine u. And the same is true with tangent. Tangent pi over 2 minus u is cotangent u. Let me convince you about these co-functions with a picture. Let's look at the first one. Sine pi over 2 minus u equals cosine u. It's kind of nice to step back and look at the original definition of the trig functions, and you'll see why this is true. Let's draw a triangle, right angle, and then label one of the acute angles u, and the sides will be A, B, and the hypotenuse will be C. So what's the other angle in this right triangle? Well, if one angle is measure u, the other one is 90 minus u, but we've been using radians mostly, so it's pi over 2 minus u. So the two acute angles are u and pi over 2 minus u. All right, I'm going to calculate some trig values by using this triangle. What's cosine u? Adjacent over hypotenuse, A over C. So cosine u is A over C. What's sine of pi over 2 minus u? That's sine of the other acute angle, isn't it? The complementary angle. Sine of pi over 2 minus u is opposite over hypotenuse, A over C again. We get the same answer. So now I think you see geometrically why this property of co-functions is true. Here are some more properties we've already seen. Sine of minus u is minus sine of u. Sine is an odd function. Odd doesn't mean weird here. It's a mathematical term, which means that precisely sine of minus some number is minus the sine of that number. Cosine of minus u turns out to be just cosine of u. It's an even function. And tangent is also an odd function. Tangent of minus u is minus tangent of u. What does this say about the graphs of sine and tangent, given that they are odd functions? Right. They are symmetric across the origin. And if you look back at the graphs of the sine function and the tangent function, you'll see that symmetry across the origin. Now, cosine is even. What does that say? Well, the graph then is symmetric across the y-axis, and if you look at cosine, you'll see that it is indeed symmetric about the line x equals 0, or the y-axis. Okay, good. We've reviewed some of our identities. Let's use them in a particular example. And this is a very common type of example in pre-calculus courses. You're given one trigonometric value, and you're supposed to find the others. And usually you have to have some more information because of the plus-minus problem. So let's assume the following. Assume that secant u is, say, minus 3/2, and we also know that tangent is positive. That's sort of an added piece of information which will be helpful. So secant is minus 3/2, tangent is positive. Well, if you know secant, you immediately know cosine. Cosine is minus 2/3, the reciprocal. So we've now calculated 2 of the 6 trigonometric functions. Cosine is minus 2/3. Now, pause for a moment. What quadrant are we in here? Where is the angle u? Its cosine is negative, and its tangent is positive. Where could u be? Right, it's in the third quadrant. That's where cosine and sine are negative, but tangent is positive. That'll be helpful in a moment. Okay, so cosine's minus 2/3. How can we find sine? The fundamental identity, sine squared plus cosine squared equals 1, is equivalent to saying sine squared is 1 minus cosine squared. So let's plug in our value for cosine squared, and we have sine squared u equals 1 minus 2/3 all squared. And that turns out to be 4/9. 1 minus 4/9 is 5/9. So sine squared is 5/9. Let's take square roots in order to find sine u. Well, there are 2 square roots, aren't there? Plus square root and minus. Which one do we take? Right, we're in the third quadrant. We want the negative square root. So sine will be minus square root of 5 over 3. The square root of 9 is 3. So now we know 3 of the trigonometric functions. What about cosecant? Piece of cake. It's the reciprocal of sine. So it's minus 3 over square root of 5. Who's left here? Well, now it gets pretty easy. Tangent. Tangent is sine over cosine. And I know them both. Minus square root of 5 over 3, all divided by minus 2/3. Cancel the 3's, cancel the minus signs, square root of 5 over 2. And indeed, tangent is positive there, isn't it, as we were told. And finally, cotangent is the reciprocal of tangent, 2 over square root of 5. And if you'd like, you can rationalize that denominator to get 2 square roots of 5 divided by 5. A nice problem. You're given one trig function and some added information, and you get all 6 trig functions. And that information was really important in determining which quadrant we were located. Okay, a little study tip here about answers. In that previous problem, we had some square roots. In fact, if you remember, the cosecant of our angle was minus 3 over the square root of 5. Well, you might look back in your textbook to check your answer for a problem like this, and you look in the back, it might not have the answer in that form. Most textbooks will rationalize the denominator. And let me remind you how you do that, although it's pretty simple, I think. You multiply numerator and denominator by square root of 5 in this case, and then the denominator becomes 5, the square roots disappear, and the numerator is then 3 square roots of 5, and there's a minus sign out in front. That's probably the answer you'll see in your textbook, with the square root in the numerator. You know, that said, again, as an author, I've noticed that in calculus courses, you rarely rationalize the denominator. I think it's kind of unnecessary myself. And in something else kind of curious, many calculus operations involve just the opposite, rationalizing numerators. It's kind of strange, I think. I don't know why we insisted as mathematicians a long time ago that we shouldn't have radicals in the denominator, but for some reason it's accepted practice now, you should ask your teacher. Is your teacher going to be upset if you put the square root of 5 in the denominator or not? Make sure you find out. Okay, let's do some more playing with trigonometric identities. Let's simplify the following expression. It's sine x times cosine squared x minus sine x. We're going to massage this and represent it with a different trigonometric function. We're going to alter this expression. Let's see how you might do it. Well, I see sine x in both terms, so let's factor it out. When in doubt, factor something. So sine x times the quantity cosine squared x minus 1. Now you look at that for a moment, you go, cosine squared x minus 1. Oh, my fundamental identity is sine squared plus cosine squared equals 1, so 1 minus cosine squared is going to be sine squared. Well, I don't quite have 1 minus cosine squared. I've got the flip. So I'm going to factor a minus sign out. So my next expression is minus sine x times the quantity 1 minus cosine squared. And 1 minus cosine squared, bingo, is precisely sine squared, and we're left with minus sine cubed. So we have a trigonometric identity here. Sine x times cosine squared x minus sine x equals minus sine cubed x for all values of x. That's always true. And trust me, this kind of simplification or manipulation comes up in calculus courses. You're often given a problem involving sine cubed, and the problem is too hard to solve because the exponent's too big, 3. But with this kind of manipulation, you drop it down to an expression where the exponents are smaller. It's a little bit longer, but it turns out it's easier to handle in calculus. Now, you could verify that previous identity with a graphing calculator. By verify, I mean you could graph both sides of that identity and look at the graph. And the graphs will be on top of each other. You won't see any distinction. It'll be the same graph because it's the same expression. But let me ask you a deeper question. Is that a proof that they're the same? What do you think? Does that really prove it? Is a graphing calculator experience, a graphing calculator picture, a real mathematical proof? I maintain it's not. And believe it or not, there are examples out there where the graphing calculator seems to indicate that the two functions are the same, but they really aren't. They actually differ by a little bit. So it's a good way to verify. I love graphing calculators. I love to use them, and I use them to verify and look at pictures all the time. But I don't accept that as a proof. The proof is what we did a few minutes ago using those trig identities. Let's do another one. Let's verify a little bit more complicated identity. The numerator on the left-hand side will be secant squared theta minus 1, and the denominator is secant squared theta, and I'm going to show that's equal to sine squared theta. So now we're back using theta as our variable instead of x. I'm comfortable using almost any variable. So here we go. And I recommend the following algorithm for verifying identities. Start with one of the two sides, do some math, and end up with the other side. So why don't I start with the left? So I start with secant squared minus 1 divided by secant squared, and now I'm going to manipulate that. And hopefully, I'll end up at the very end with sine squared. Let's hope. Here we go. How about, what can I do about secant squared in the numerator? Well, I remember an identity. Tangent squared plus 1 is secant squared. That means that secant squared can be replaced with tangent squared plus 1. So I'll do that in the numerator, and I have tangent squared plus 1, that's the version of secant squared, minus 1, all divided by that same denominator. The ones cancel, and I'm left with tangent squared divided by secant squared. But now watch. If secant's in the denominator, and secant is the reciprocal of cosine, I can pull it up to the numerator as cosine squared, right? Cosine and secant are reciprocals of each other. So now I have tangent squared times cosine squared. We're getting there. Well, let's change tangent squared to its definition, sine squared over cosine squared. The cosine squareds cancel, and we end up with sine squared. Whew. A lot of trig identities there, a lot of work. But we started with the left-hand side, did some math, and got the right-hand side. Okay, so I do recommend that. In a minute, I'll show you why I really recommend that. Something else to point out. True, this is an identity, but it's actually not true for every value of theta. Sine theta, or sine squared theta, is defined for all theta, no problem. But notice that secant is not defined for all theta. Remember, secant's 1 over cosine, and hence, if theta say pi over 2, it's not defined. So when you write these identities, you're assuming that you omit the points that are not in the domains of the functions, okay? That's just sort of assumed. Something else to point out here, there are many ways of doing these problems. You might not have chosen the steps that I did here to solve it. In fact, as a teacher, that's one of the great things about being a math teacher. I learn a lot of mathematics by teaching mathematics. My students often solve problems in very interesting and different ways, and I'm sometimes, whoa, where'd that come from? How'd you do that? And then I discover, in most cases, they're right, and it just did it a better way than I did. Let me show you this problem again. Let me show you a different way. And heck, there are probably lots of ways of doing this problem. Let's start again with the left-hand side, secant squared minus 1 divided by secant squared. I'm going to manipulate it a little bit differently. Oh, this is a fraction. I can split this into 2 pieces. Remember, you can separate numerators. So it's secant squared divided by secant squared minus the quantity 1 over secant squared. And now secant squared over secant squared is just 1. 1 over secant squared is minus cosine squared. They're reciprocals. And 1 minus cosine squared by the fundamental identity is sine squared. Hey, that way was easier than the other way, I think. So you see that you can be very creative in these problems. They're kind of fun, I think. Start with one side, play some games, end up with the other side. And in our workbook, you'll have the chance to try some more of these identities. I think you'll enjoy doing them. Now, I mentioned as a technique for solving these that you start with one side and go to the other side. Here's something I see often in students' work. They'll start with the identity at the top, and they'll start manipulating both sides, like this, doing all kinds of work until they end up with something that's true. They end up with something that's true, and then they declare, because I arrived at something that's true, what I started with also must be true. Now, is that logic correct? You start with what you want to prove. You start with your goal. You do some mathematics, and you end up with something that's true, something like 1 equals 1. Does that mean that what you started with is also true? Well, that would be okay if you could reverse your steps and start with something that's true and get back to what you want to prove. But in general, it's not correct to start with what you want to prove and work with both sides simultaneously. Let me show you a simple example of a false proof. You'll see that if you start with what you want to prove, you'll make a mistake here. So suppose somebody tells you, hey, the following equation is true. Sine x equals the square root of 1 minus cosine squared x. Let's try to prove that. This is a false proof. Sine x equals square root of 1 minus cosine squared. I want to prove that. So the incorrect method would be start with that statement and manipulate it. Square both sides. Sine squared equals 1 minus cosine squared. Oh, and that's the fundamental identity, sine squared plus cosine squared, which equals 1. I arrived at a true statement. So I did some math. I ended up with a true statement. Can I conclude that the original statement at the top is true? No, That statement actually is false for some x values. Sine x does not equal the square root of 1 minus cosine squared x for all x. For example, if x is 3 pi over 2, then the sine of 3 pi over 2 is minus 1. But the cosine of 3 pi over 2 is 0, and the square root of 1 minus 0 is the square root of 1, or 1. So the left-hand side is minus 1, and the right-hand side is 1. So that's not an identity. It's not true for all x. Isn't that interesting? This technique of starting with what you want to prove, starting with your conclusion and going down to something that is true, that's not good mathematics. I suggest you start with one side, do some math, and end up with the other side. All right. You be the teacher for a moment. You're giving an exam, and a student comes running up to you and says, Professor, I have the answer of log absolute value of secant theta. That's my answer. But the answer key says that the answer is minus log of cosine theta. Did I get the problem wrong, teacher? So the student thinks the answer is log of the absolute value of secant theta, but the answer key said minus log absolute value of cosine theta. Is the student wrong? What should you say as a teacher? Well, you should be, hey, don't worry, you're right. Those are the same. In fact, minus log absolute value of cosine is the same as minus 1 times the log. And now we remember those logarithm properties we studied a few lectures ago? Yeah, that exponent can motor up, that minus 1 in the front can motor up to be an exponent. So it's log absolute value of cosine to the minus 1 power. Cosine to the minus 1 is 1 over cosine, also known as secant. Wow, those are the same. It's the same expression. And if you think that's kind of an obscure example, I got this out of a calculus book. There are problems in calculus that end up with this answer. And the book has one version of the answer, and a student might come up with the other version. The student shouldn't panic. The student is right. Both answers are equally good. Okay, let's verify another identity. I think these are kind of fun. Secant x plus tangent x. Let's show that that's the same as cosine x over 1 minus sine x. And we're going to see a technique here very similar to rationalizing the denominator. Very similar technique. I'm going to start with one side, do some math, and end up with the other side. I'm going to start with cosine x divided by 1 minus sine x. Okay, so what do? I'm going to multiply numerator and denominator by 1 plus sine x. That's kind of the opposite of 1 minus sine x. You'll see in a minute why that was a good choice. So the numerator becomes cosine x times the quantity 1 plus sine x. The denominator is 1 minus sine x times 1 plus sine x, which is 1 minus sine x squared. Ah, you recognize that guy? Yeah, that's cosine squared, isn't it? That's the fundamental identity being used yet again. So the numerator is cosine x times 1 plus sine x. The denominator is cosine squared. We can cancel some cosines, and we're left with 1 plus sine x over cosine x. And now that can be ripped apart as a fraction as 1 over cosine plus sine over cosine. Well, 1 over cosine is secant, and sine over cosine is tangent, and that's what we wanted to prove, wasn't it? That cosine over 1 minus sine does indeed equal secant plus tangent. Now, I did it kind of a clever way with that little trick. I invite you to try to prove this some other way. As I said earlier, there are lots of ways of proving an identity in trigonometry. Let's show an example from calculus again. I picked this problem out of a calculus book. And it said the following, that tangent to the fourth of x equals tangent squared x times secant squared x minus tangent squared x. Do we believe that? Is that an identity? Can we prove that? Well, let's try it. Let's start with one side. How about with tangent squared x secant squared x minus tangent squared? And let's see if we can end up with tangent to the fourth. So how about if I do the following? Let's factor out tangent squared. And I'm left with the quantity secant squared minus 1. Oh, I recognize that. Tangent squared plus 1 is secant squared, so secant squared minus 1 is tangent squared, and we have tangent squared times tangent squared equals tangent to the fourth. Now, why was this in a calculus book? Well, again, this is this idea of reducing a power. Tangent to the fourth, that's to a high power. 4 is a high power. And we've expressed that using just squares. Tangent squared, secant squared. That power reduction skill comes into play in calculus courses. Okay, you be the teacher for a moment. A student wants to know the difference, or how do you explain the difference between certain notations? I found teaching math that a lot of the problems that come up are caused by notation, caused by issues of not understanding how mathematicians write certain things. We've seen examples of this earlier. Remember when we had the inverse sine function, sine inverse, it was sine to the minus 1 power. That can be very misleading for people. They might think that's 1 over sine, cosecant. No, it's not. That's why I prefer using words like arcsine. So here's some other notational pitfalls that you might come across. Sine of x squared. And this would be written without any parentheses generally. It would just be sine x squared. And then you also see sine squared x. So now the 2 is moved inside. And you've also seen expressions where sine of x has parentheses around it, and then it's squared. Now, are these the same? Are these different? What's going on here? Well, sine of x squared without any parentheses at all is equivalent to sine of the quantity x squared, as if you had parentheses around the x squared. And in fact, it's probably preferred to put those parentheses there just to be extra sure the reader understands that it's sine of the quantity x squared. Whereas sine with a 2x, that means sine with parentheses all squared. Unfortunately, mathematicians don't write it that latter way, do they? They like to write it as sine 2x. That's just the way it is, and I've become comfortable with it over the years, and my students, unfortunately, have to become comfortable as well. So let me pose some questions for you. We've been verifying identities. Suppose somebody comes up to you and says, hey, is this equation an identity? Is it true or is it false that sine x plus cosine x equals 1? Is that an identity? Is it always true? Now, it kind of looks familiar, doesn't it? Remember the fundamental identity, sine squared plus cosine squared is 1. But this is a different equation. Is it true for all x? Well, I bet you suspect no. You're probably saying, no, I bet you that's not true. But here's a question. How do you prove that it's not true? And this is sort of a general mathematical question. If you want to prove something is true for all x, you have to do the kind of work we've just been doing the last few minutes. You have to start with one side and get to the other side. That's hard work. That's, as I like to say, that's heavy lifting. It takes some work. You've got to play with identities, etc. But now it's a different question. Now we suspect that this is false. How do we show something is false? Well, it's much easier. All you have to do is find a single x value that messes up the equation. In other words, show that it's not an identity by finding an x value for which it's not true. In this case, sine x plus cosine x equals 1 can be shown to be false by picking, say, x to be pi over 4. Let's try it out. What's the sine of pi over 4? 45 degrees pi. Oh, square root of 2 over 2. What's the cosine? Square root of 2 over 2. So the left-hand side is square root of 2 over 2 plus square root of 2 over 2, which adds up to the square root of 2. What's the right-hand side? 1. They aren't equal. So it's not an identity. Of course, you might ask a deeper question. Is it ever true? For example, if x is pi over 2, it is true. And in fact, that's an example of a trigonometric equation. And that will be the topic next lecture. In other words, you're given an equation like sine x plus cosine x equals 1, and you ask yourself, are there x values for which it is true? It's not true for all x, but it's true for some x. Here's a simpler one. Sine x equals 1/2. Is that true? Well, it's not true for all x, of course not. But there are some x values for which this is true. So next time we'll talk about these trigonometric equations where the goal will be, given an equation like this, find x. Find the value of x that makes it true. All right, I'll see you next time. Thank you.